Things going all right? All right, so let's continue our discussion here with linear transformations. Finish up the handout from last time. Got a new one for today. So we did this problem near the end of class last time, but we didn't do the general rule for the transformation of x, y. We did the transformation of 2, -3. And again, the idea was that we could figure out what the transformation is for 2, -3, since we know what the transformation does to v1 and v2, and then we can write 2, -3 as a linear combination of the basis vectors that we're given, -2, 1, and 1, 3. We didn't go through all the computation, but that was the idea, that we can remember the transformations break up over sums and constants pull out, so that you can take, pardon me, a transformation of a linear combination and break it down into the pieces that are in the combination, the vectors that are in the linear combination part. So if we wanted to find a general rule for transformation of x, y, we would need to do the similar thing that we did here. We would want to solve, pardon me, that system -2, 1, 1, 3, and then for some arbitrary x, y, and figure out what we would need for our constants in terms of the x and in terms of the y. Which we could do by hand, but this gives me an opportunity to show you another quick computer program that some of you who are numerical have seen in the last few class periods, and that's GeoGebra. GeoGebra is a nice program that you can use to do symbolic algebra things. I actually do lots of different things, but what I want to use it in particular right now is symbolic algebra things. So the site address is geogebra.org, and we want to use the classic version of GeoGebra, which for some reason they've taken off their main web page. But if you go to /classic, it'll go to that particular one. When you load it up, it comes up with what they call an algebra window and a graphing window. We're not going to use it for the graphing part for our purposes. But if you go up to the menu, you can switch what the view is. Under the menu, there's a view. We want the computer algebra system part, the CAS part, because that'll allow us to do symbolic algebraic manipulation rather than having to have numbers like what you'd have to have out your calculator. Okay. So again, the matrix that we just set up a second ago was at -2, 1, and an x, and a 1, 3, and a y. And we want to row reduce this thing, right? So over here in GeoGebra, if I use braces around the whole thing and then write each row as a brace, a list of things with braces, I can make a matrix. So my first row here would be -2, 1, x. And then the second row would be 1, 3, y. And then notice it'll put it in a matrix form for us. It'll use parentheses rather than brackets, but it puts it in a matrix. So if you've done a little bit of computer programming, basically it's made a list of lists. And it recognizes, for GeoGebra, when they have the same size like that, it'll just make it into a matrix. So the idea, again, is to figure out what the coordinates we would need for the vector x, y in terms of the basis -2, 1, 1, 3. So we would need to row reduce this thing. We've talked about that before, right? But I want to row reduce it with letters rather than numbers, and I really want to be lazy and don't do it by hand. That's why I'm doing this, okay? Notice that if I start typing the word row, and the actual command is reduce row echelon form, I want the reduce row echelon form of the matrix that I just typed in. If I hit enter on that command, it'll open it up, and notice that it tells you what the form of the function has to be. So it needs to have a matrix inside of there. If I hit enter again, it'll pop that up and leave it in there for you to remind you that you need a matrix in there. The matrix we have is in line 1. So if I just refer to it as number 1, it'll go back and grab it. You could also assign it a variable name and then refer to the matrix by name. We're not going to use it very often, so I'm not going to go through a lot of the different details, but that will give it to you. So in this case, pardon me, when we have some arbitrary xy, I now know what the linear combination is that I need to use in terms of the basis vectors that we have. Okay, I want to write this down so that I can come back and refer to it. We've got negative 3x plus y over 7, and the other one was 0, 1, and then x plus 2y over 7. So remember, the problem asked us to find a general rule for the linear transformation, given that I know what the transformation does to the negative 2, 1 vector and what it does to the 1, 3 vector. So pop back over here real quick. By what we just did, if I have some arbitrary xy that's in there, then I know these are the coordinates of that vector, whatever the xy is, in terms of the negative 2, 1 and the 1, 3. We know that linear transformations break up over sums and constants pulled out. These are just, if I'm given x and y, these are just constants. So we can rewrite this as negative 3x plus y over 7 times t of negative 2, 1, and then plus x plus 2y over 7 t of 1, 3. This is the constant we would use on the 2, 1 vector in our linear combination. This is the constant we would use on our 1, 3 vector in our linear combination. And then we reuse the properties of transformations, linear transformations, that allow us to break it up over sums and pull the constants out. Let me expand this so we can actually see more. Okay. Notice that we know what the transformation does to negative 2, 1, and we know what the transformation does to 1, 3. So now we can plug that in. So this will be negative 3x plus y over 7 times the vector 1, 2, 0, and then plus x plus 2y over 7 times the vector 0, negative 3, 5. And then we can put everything back together. The first component will be what? I'll multiply that times the negative 1. This is plus a 0 on the end, so all we get is 3x minus y over 7 for the first component, right? This one will be negative 6x and then minus 3x. So I'll get negative 9x. Then I get plus 2y minus 6y. So we get minus 4y all over 7 for the second component. And the last one we just get, that's a comma, a very ugly looking comma, 5x plus 10y over 7. Because I got a 0 in that last component of the first one. So now we have a rule. That looks like it says 71. That's a comma down here. Now we have a general rule for the transformation based on, again, the basis vectors that we have. That okay? So far so good? All right, so basically we're just trying to find the rule. So let's see if we can apply it to the next one as well. Here's the setup that we have. We've got 3 vectors in R3. We know what the transformation does to each of those basis vectors and sends them to a vector in R2. It asks us to find the general rule. So what matrix, what augmented matrix did we set up that we want to row reduce to start with? Okay, good. So again, the idea here is just going back to the same idea that we did in the previous chapter, that we're finding coordinates of a vector relative to a basis. So the basis, well, we can check that we really do have a basis for R3 here. We do. We'll see it when we row reduce. But all we're doing is that same concept, right? We're using the fact that we can find the coordinates of the XYZ vector in terms of the basis vectors that we have, right? And then to find the coordinates, we just row reduce this matrix. So again, let's use technology to help us rather than having to do this by hand. And I've forgotten already what the matrix was. All right, so the first row was one. Back up here. What was the first row again? 1, 3, 3?
1, 2.
1, 2, 3. Thanks. Row. Yeah, we're doing the rows. And then X is right. Was the first one. The second row is 2, 9, 3. And then Y. And the last one 1, 0, 4. Is that what you're saying? I just can't hear you from here. Sorry. Let's see. That what we had? Okay. So again, we got to type it in by row to be able to use this. And again, the only reason why I'm doing this is to use the technology. You could row reduce this by hand. It's just a little bit more work, right? Trying to say this is work here. All right. All right. So then, again, the command for this is reduced row echelon form. And then that matrix is up in line 3. Notice on the left-hand side, it's numbering the lines. So you can refer to previous lines by their number. Bump that out a little bit. I'm just going to write down the answers that I need. The 36x plus 8y plus 21z. The 5x minus y minus 3z. And the 9x minus 2y minus 5z. All right, so those are the... We use this one as our coefficient for the first vector. This one for the second. This one for the third. So going back over here... Pardon me. So again, we row reduce this thing. Whatever that was. 36x plus 8y plus 21z. 5x minus y minus 3z. And 9, 2, and 5z. Okay. So again, these numbers tell me how to write an arbitrary XYZ vector as a linear combination of the 1, 2, 1, the 2, 9, 0, and the 3, 3, 4. So again, get this out of my way. Things. And then, of course, it just shifted everything. It's fine. So again, if I want the transformation of x, y, z, I would use the first constant times the output for the 1, 2, 1. We would do the second constant times the output for the 2, 9, 0. And finally, the third constant times the output for the 3, 3, 4. The output for the first vector is 1, 0. The output for the second vector is negative 1, 1. And for the third vector, is 0, 1. And now it's just a matter of combining the vectors. Your first component here will have negative 36x minus 5x is negative 41x, and then there's nothing in the other one, so I get a negative 41x. 8y plus y gives me a 9y. 21z plus 3z gives me 24z. And then for the second component, there's no second component. I mean, this one just gives me a 0 when we do the multiplication. So I only need to look at the last two. 5x plus 9x is 14x. Minus y minus 2y is minus 3y. Minus 3z minus 5z is minus 8z. Just combining the vectors. Just doing it each term at a time. Is that okay? Where I'm getting those? Notice when I'm doing the first components, I don't need to worry about this one because there's a 0 in the first component here, right? So I'm just doing that times the 1, that times the negative 1, combining like terms. I just did the x's, y's, and z's separately so I wouldn't have to think about it all at the same time. The negative 36 minus 5. I've got 8 plus 1 and 21 plus 3 for that. And then for the second component, I didn't have to worry about this one. So I just focused on the last two because that had zeros in it. Made my simplifying easier. Is that okay? All right. So now that we have a general rule, we can plug in the 7, 13, 7 and get our answer. At that point, it's just a matter of plugging in the 7 for the x, the 13 for the y, and the 7 for the z. So your transformation of 7, 13, 7. And I'm not going to simplify the arithmetic. I'm just going to plug it in. Again, put 7 in for x, 13 for y, 7 in for z. And whatever those numbers turn out to be. That okay? Ma'am? Okay. Pardon me, sorry. Okay. All right, so let's go on and talk about the additional concept here that we have on this handout before we go on to some new stuff. And that's the idea of composition. So composition of linear transformations is just like composition of functions that we've done before. So if I've got a function going from u to v, and then another function going from v to w, the idea is I'm going to take something in u, plug it into the first function, get something out in v, I'm going to take that output and now use it as an input. All right, usual composition ideas. The way, of course, we write composition is this notation because we think of this as the inside, that's the outside idea, right? So we write it kind of backward from what you think about it. At least I think it's kind of backward from what you think about it. But the way this would be defined then is if I've got the composition of this for some vector in u, well, again, you know how composition works, and it works exactly the same way for linear transformations. I do T2 of T1 of u. Take your input, plug it into the first function, take that out, plug it into the second function. All right. So in this one, it wants us to find the composition of these two things. So let's do it directly and then see if we can do it using our knowledge of matrices that we talked about before. So if I want T2 of T1, well, notice that things that are going into T1 are two-dimensional vectors, right? Actually, let's write that down to start with. T1, its domain is R2. Where does the codomain end up? What size vector do you get out in that one? R3, right? Oops. Why am I writing those in subscripts? Those are superscripts. Right? I put in a two-dimensional vector, I get a three-dimensional vector out. Your T2, what are you doing? Yeah, it's R3 to R2. Good. Putting a three-dimensional vector in and getting a two-dimensional vector out. Just making sure that we understand those things. So again, well, I didn't write it down the way I probably should have to start with. This is T2 of T1 of XY. The output for T1 of XY now becomes our input for T2. Our output for T1 is the vector 2x negative 3y x plus y. So now when we do our composition, just like what you do a composition for other functions, it just looks a little bit nastier because we've got multiple components and things, but the concept is the same. This goes in wherever you see the x, this goes in wherever you see the y, this goes in wherever you see the z. Right? Okay. So what do you get in the first component then? Yeah, you get 2x plus 3y, right? The 2x goes in for the x, the negative 3y goes in for the y. What do you get for the second component? Yeah, so you get negative 3y plus the x plus the y, right? That's a y. Sorry, yeah, that's a y. Right? Because this part, this is going in for the y, this is going in for the z. And we get x minus 2y here. All right, so let's notice something here. This is something we're going to come back to later on. Let's write down the matrices associated with each of these transformations. So we used an A last time, but let me use a slightly different notation. Let's use brackets around it. We'll call that the standard matrix for the transformation. We did this last time. Since T1 is going from R2 to R3, what size will the matrix be? 3 by 2? Good. And then how do we fill in the rows? How do we fill in the rows? So remember, we look at the components. How do we fill in the rows? Yeah, the coefficients on the x's and y's and so on down the line, right? What's the first row going to be? The second row will be, and the last row will be 1, 1. Good. For T2, what size matrix will T2 be? Or the matrix for T2 be? 2 by 3. What will the rows there be? Yep. And then 1, 1, right? We will need an x, y, z in that case. What do we end up with when we multiply those two matrices together? Oops. What size matrix will you have? Two by 2. Okay, what do you get for your entries? What's the upper corner, left corner entry going to be? Two. Yeah, it's 2, right? Because I get 2 times 1, negative 1 times 0, 0 times 1. Next one is going to be it'd be 3, right? Because it'll get 1 times 0, negative 1 times negative 3, and 0 times 1. Lower left, a 1. Lower right, minus 2. Let's go back over here. Look at your composition. Your composition goes from what to what? What's your input space? Well, for in this specific example, what's the input space? R2. What's the output space? So R2, right? So what size matrix do we end up with? 2 by 2. What is the matrix? Reading it off from the function we found. 2, 3, 1, negative 2. Does that look familiar? Does it look familiar from what we just found? Yeah, it does, doesn't it? Okay. All right. This is not a coincidence. We could have done the transformation in this fashion. We could have found the matrices first, multiplied them together, and that would give us the matrix for the composition, and then got the rule. Could have done it that way too. All right. We're going to come back to this idea later. So notice in the next one, we're not going from R3s to R2s or R2s to R3s or anything along those lines. Your T1 is going from the set of 2 by 2 matrices to the real numbers. And we're going to take the trace of the matrix, and it's been a while since we've talked about that, if we've talked about it at all, because there's not a lot we do with trace for what we've done. Trace just means you add the main diagonal. That's all trace means. Take the main diagonal entries and add them together. So for example, for this matrix here, we would just take the A plus the D. Okay. That's all trace means. Okay. So T1 does the trace, T2 does the transpose. So let's answer part B first. Can you do the composition T2 composed with T1? So T1 again takes a matrix and gets out what? What kind of an object? A real number. Am I allowed to put real numbers into the second one? No. Okay. So I can't do T2 composed with T1. Okay. So I can't do the composition in the other order. Because the spaces don't match up. Okay. All right, so let's see if we can do T1 composed with T2. Again, composition says work inside out. What does T2 do to the matrix? Transposes it. And then what does T1 do to the matrix? To trace, and the trace in this case, again, is just going to be A plus D. So notice that taking a transpose just doesn't change the trace at all, because it doesn't change the main diagonal. So you get the same function as you would have gotten from T1. It didn't actually do anything. So again, doing these composition is exactly what you would expect. Let's do one more example, and then we'll talk about some new stuff. Let's look at this last one here. Let's say we're on a function space that we can actually take derivatives. That'd be helpful. So we're going to use this d function as the derivative of f, the I function is the integral of f, but we're going to set the definite integral going from 0 up to x. That's some terrible notation by me. I've got x meaning two different things in the same thing. This really should be like a t here and a t here. It's bad notation. Okay. Those x's mean different things, right? One's the variable of the integration, the other one's the limit of integration. All right. So the first one says I want to find d composed with I, and then the second one says I composed with d. And it says let's do it for these three different functions. So in the first one, if you do d composed with I, which function are you going to do first? You do the I function first, right? Now, what does the I function do? What does this limit of integration do? If I didn't have the limits of integration on there and just said integrate, you would find a general antiderivative and get a plus c on the end, right? But since I'm starting at 0, what does that do for your constant? What does it make the plus c equal? So I'm asking for a specific antiderivative, not a general one, right? So what does that starting at 0 actually do to the arbitrary constant? It's not arbitrary anymore. It makes it 0. It makes it go away, right? Because remember, when you do a definite integral, do you ever put the plus c on the inside when you do the definite integral? No. Right? You just need an antiderivative for fundamental theorem calculus. So I wouldn't even put the plus c in there. So that putting a 0 there just is going to get rid of that arbitrary constant part. So let's see what happens here. If I want integrate and then differentiate, well, integrating gives us 1/3 x cubed plus 3/2 x squared plus 2x, and then I don't have a constant on the end, right? Agreed? Okay. And then it says differentiate it. What do I end up with? I end up back where I started, right? If I integrate and then differentiate, I'm going to end up back where I started. Is that going to change for the other ones? No, we'll get the exact same thing, right? You'll integrate, you'll get negative cosine x for the f of x, and then you differentiate, you get back to sine, right? So that one's always going to get you back to f of x. But what happens if you do it the other way around? What happens if we differentiate and then integrate? So let's do the first one. What happens when you differentiate f of x in this case? It's not a trick question. If I do this function, what do we get? 2x plus 3. And then if you integrate, what do we end up with back? Yeah, x squared plus 3x, no constant, right? I lose the constant. Right? And the same thing will happen for the other ones. This is not the same thing we started with, right? If you did the same thing for the e to the x plus 3, you would end up with e to the x when you're done. You lose that constant that's on the end. So even though we think of differentiation and integration as inverses of each other, they're not quite, right? Almost, but not quite. And part of the reason why we know that is because if two functions have the same derivative, they didn't have to start off being the same derivative, but they did have to be within a constant of each other. Notice that what we lose is the constant information here. I'll work backwards. That's the whole point of this one is, even though we think about these ideas as being inverses of each other, they're not quite inverses of each other. Anyway, any questions on doing the composition at all? We're going to come back to it. In particular, we're going to come back to that idea of being able to do composition through. Did I send this to you already? Yes, you did. Okay. Thinking about doing composition through what matrix multiplication. All right, so let's talk about a couple more concepts here as far as matrices go. And then there's going to be the concept of kernel and range. Range is a word you've heard before back in algebra class, but kernel probably is not. Several years ago, I had a student, every time I say the word kernel, he would laugh. I have no, I'm guessing he was thinking about Kentucky Fried Chicken. I don't know why. But it was every time I would say kernel, it was laughter. And we talk about kernel not only in linear algebra, we also talk about it in abstract algebra, and handy for both classes. So there was a lot of laughter. So, in any event, range is what you expect range to be from what you learned back in algebra class. Remember, range is your set of all possible outputs. So we'll put that up as a math definition here in a second. But remember, when you think about range back in algebra, usually you thought of looking at a graph and then see what the y values were taken up by your graph for range, right? So all possible outputs, same idea here, okay? Kernel is a little bit different. Kernel is a set of vectors. We denote kernel with KER of t. So that's going to stand for our kernel of t. This is going to be the set of all vectors in your input space that get mapped to the zero vector. And just for emphasis sake, that zero vector will be in your output space. So the kernel is a set of everything that gets mapped to the zero vector. So to give you a quick example of something that will be a little bit non-standard, I guess, ideas. If your vector space is, just as a quick example, if your vector space is your set of differentiable functions, that's what we use by the C1, right? Set of the differentiable functions on the real line. And if we use just the differentiation operator, I'll just write it as differentiation. If we use the differentiation operator, and when I use the word operator, I mean it's a transformation that goes from a space to the same space. So when I say operator, it just means that it's just a map from a space to itself. All right. If I use the differentiation operator and I want to know what its kernel is, I'm looking for all functions that have derivative 0. What kind of functions have derivative equal to 0? Constants, yeah. So your kernel here is the set of constant functions. So it just gives you a quick example of something that is a kernel, okay? So again, it's the thing that, say everything that maps to 0. In this question, it's just asking you what kind of functions have derivative 0. Constants. Range, we just said range is a set of all possible outputs. Notation for range is ran of t. This is going to be a subset of your codomain. Remember, it's a set of all possible outputs, so that means there must have been something in the domain that got mapped to W. So it's the set of everything in W that has a pre-image. We call this a pre. V would be a pre-image. Okay. It's the set of everything in W that gets hit by something. I can plug something into the function and get W out. Okay. So to give an example of that differentiation operator again, if I have the function 2x, tell me something that maps to 2x through differentiation. X squared, right? So 2x would be in the range, is what we're saying there. Right? However, something that wouldn't be in the range would be absolute value of x, because there's nothing that has a derivative that's in this set that has a derivative of the absolute value of x. Okay. All right. So anyway, that's the idea here. Okay. All right. So range is just a set of functions that get hit. Now, of course, absolute value is not in our codomain in that case, so it's not kind of a bad example, but that's the idea. All right, so let's do this first example here that we have. It's asking you, are these two vectors in the kernel? Is 3, 2 in the kernel? Is 5, 10 in the kernel? Well, those should be pretty easy questions to answer because, again, the kernel is a set of everything that gets mapped to 0. So how do you think we can check if those things are in the kernel? Do I want to set it equal to 0 or plug it in and see if we get 0, right? It's a set of everything that the kernel is a set of everything that gets mapped to 0. So we just need to check t of 3, 2 and see if we get the 0 vector. I get what? 6 minus 2 is 4, and then we get whatever negative 24 plus 8 is negative 16. Is certainly not 0, 0. So 3, 2 is not in the kernel. T of 5, 10. I think I do get 0, 0 in this case. So 5, 10 is in the kernel. Oops, is in the kernel. So checking whether or not something is in the kernel, pretty straightforward. You literally plug it into the transformation and see if you get 0. Whatever the 0 vector happens to be in that space. Last part there says, can we find a basis for the kernel? Good question. If I want to find a basis for something, I guess I'm pretty much assuming that it must be a space of some sort, right? It must be a vector space. I'm going to know what a basis for it. We didn't prove that at all, but you should be able to show that the kernel really is a subspace of the domain space. So we'll talk, I think I might do that later, but in any event, we should be able to show that the kernel really is a subspace. Remember, subspaces closed under addition, closed under scalar multiplication, right? So we'll talk about how we can prove that later, but let's just talk about how we would find a basis, assuming that it is a subspace. The kernel is the set of everything that gets mapped to the 0 vector. How might we find the set of everything that gets mapped to the 0 vector for this transformation? Now we set it equal to 0. Yeah, so notice again here with this particular transformation, we should be able to solve a matrix equation, right? What is the standard matrix for this one? Let's do that first. What will be your first row? And the second row will be negative 8, 4, right? We want to find all vectors, I'll call it x in this case, so that t of x is equal to 0. But we can do that in this case by solving this matrix equation which we've done probably more times than we can count this semester, right? Notice that the second row is -4 times the first row. So this is the reduced row echelon form of this is going to look like this. How many free variables do you see? 1. So what dimension will the kernel have here? 1, right? The kernel is just this, the solution set here to the homogeneous system, or the null space of this matrix. It's another connection here that we're making, right? Notice how much stuff just goes back to solving systems of equations over and over and over and over again, right? Well, what will your solutions look like? If your x2 is t, your x1 would be a half t. So a basis for the kernel here. Yeah, it'd be a L, and just a basis, then we'd just get rid of the t, right? So the basis would just be 1/2 1. Or you could use 1 2. Either of those would work, right? Any multiple of that will work. Notice that even though we phrased it as a different question, same idea that we've had before, right? Set it equal to 0 and solve. Questions on that at all? Okay. Notice that we're asking the other question for this part. It's asking, is 1 -4 in the range? Is 5 0 in the range? And then, of course, asking us from there, can we find a basis? If I want to know if something is in the range, notice again, the range is defined as I can find a vector. I can find a vector in the domain that maps to the given vector, right? So going back down here, if I want to check that 1 -4 is in the range, what do you think we should do? So again, we want to think of the whole idea is, can we find some x in our codomain or our domain so that the t of x is equal to the vector 1 -4? That's the question we're asking, right? If it's going to be in the range, right? Okay. What do you think we need to do? Yeah, do the same kind of idea that we just did, just change the 0 0 vector to what? 1 -4. All right. Do the same exact thing. Can we solve that system? Looks like we can, because again, we already noticed that this row is what? -4 times the first row, and that's -4 times that, right? So if you do your reduced row echelon form here, you would end up with 1 -1/2 and 1/2 0 0 0, right? So again, our solutions here, you'd have an x2 as t. Your x1 in this case would be 1/2 plus 1/2 t, right? Yeah. So can you give me one vector in particular that maps to 1 -4? You find one solution. Well, we can find infinitely many, so can I find one? Yeah. What can I plug in for t to just give me one of them? I could plug in 1, I could plug in 0. There's lots of different things I could do, right? So we could check, if I do t of, let's just do 1/2 0, plugging in a half for, or a 0 for t. If I go back up, that was our definition, wasn't it? And we really do get 1, -4 in that case. There are many examples, right? I just plugged in 0 for t to find 1. This shows that it really is in the range. If you tried 5, 0, it won't work. What I want you to think about for Monday is the last question. Can you figure out how to find a basis for the range? So actually there's technically there's 3 things I want you to think of for Monday. 1 and 2 are kind of related. Can you think about why kernel and range are subspaces? And then think about how you would find a basis for the range. If you can find a basis for the range. Put it that way. All right. We don't have class on Friday because of celebration of scholarship. Kind of forgot about that part. So we'll talk about more of this stuff on Monday. If I don't see you before then, have a good one.